This is 1985, number 2. This would be an Fnet equals 0 problem. Two 10-kilogram boxes are connected by a massless string that passes over a massless frictionless pulley as shown above. So that would be ideal. The boxes remain at rest with the one on the right hanging vertically and the one on the left 2 meters from the bottom of an inclined plane that makes an angle of 60 degrees to horizontal. The coefficients of kinetic friction and static friction between the left-hand box and the plane are 0.15 and 0.3 respectively. You may use G equals 10 meters per second squared. What is the tension in the string? So looking at this, the tension is going to be the same because it's an ideal pulley. Which side do you think will be easier to deal with? The weight that's just hanging or one that's at an incline? I'm going to deal with the one that's just hanging. So I'm going to do a free body diagram for this one. It's going to have T going up. It's going to have mg going down. I'm going to say Fnet equals 0. I'm going to take my up minus my down. And my tension is going to be equal to 10 times 10 or 100. All right, part B. On the diagram below, draw and label all the forces acting on the box that's on the plane. So this box has tension in the direction of the incline, parallel to it. It has normal, perpendicular. It has mg going straight down, and then this one's trying to pull it up. So friction is in that direction. Friction is the retarding force. It's opposing the motion. All right, they want us to find friction. I'm going to take my free body diagram and spin it. So I'm going to have normal going straight up, tension, which I know going to the right, friction, which I don't know going to the left, and mg at an angle. So this is 60 degrees. This would be mg sine of 60, because it's the opposite. This would be mg cosine of 60. So it's at rest. So if I want to find friction, I'm going to do Fnet equals 0. So I'm going to say down the incline, parallel to the incline, Fnet is equal to 0. So I'm going to say, I'm going to take right minus left. I'm going to say T minus F minus mg sine of 60 is equal to 0. And so I'm going to add F to the other side, and I'm going to have T minus mg sine of 60 is equal to F. So I'm going to plug in what I know. We change the color so we don't get confused. I have 100 newtons minus 10 kilograms times 10 meters per second squared times the sine of 60. And so this is going to be 100 times sine of 60, which would be 87. And so I'm going to get a force of friction of 13. How is this tricky? Well, you can't use mu n. You can't go, okay, I know friction, I can't use mu n, because this is not true in this case. If you remember, for static friction, this is less than or equal to. So friction is as much as it has to be. And unlike the friction lab where we pulled until it just let go, we don't know that it's at that limit. So let's see what it would be, what we would get if we used mu n. Well, in the y direction, Fnet is also equal to 0. So I know that n is equal to mg cosine 60. And so if I plug in my mu, which is 0.3, and my n, which is going to be mg cosine of theta, I have 10 kilograms, so 10 meters per second squared first, cosine 60. If I put this in my calculator, which of course is located across the room, instead of 13, I get 15. So what does this tell me? That with this coefficient of friction and this normal, the friction could be as much as 15. But in this problem, it only needs to be 13 to balance that force.